talking about colours, next we have Mihai, who, as I said, is going to talk about colours. So please give a warm welcome for Mihai.
I think that everyone here loves a good rainbow. Is that true? It's not that hard to get one. You'll find that any ray of light can be split into a rainbow to put it through an optical prism. Still, if pink is your favorite color, you might be unsatisfied with nature's palette because pink is not in the rainbow. So we'll try and figure out why these red to violet rainbow colors are so special. We want to learn something about our colors, so we should start with a bit of introspection. So I want you to concentrate on the picture. And now I want you to think of how many words you would use to describe your memory of that sun's color. I think everyone remembers it was bright, light red. And these are three very intuitive and easy to remember characteristics. They're called brightness, saturation, and hue. And furthermore, if you assign scales to these, you can use them to describe any color. And you won't only be using three numbers. And you won't. That means that if I give you a measure of brightness, a position in the rainbow, which is called hue, and a certain amount of white to add, which is called desaturation, you should be able to imagine a certain color. And there's a biological reason why we find that simple. You know we have three types of cone cells in your eye, and they respond differently to different colors. And behind the retina, you have some neurons that add up the three signals, and they encode some different coordinates. They're quite similar to brightness, saturation, and hue. So we should now understand that colors live in a three-dimensional space, just like us. If you look around, try and see if you believe me. Tree doesn't have a profound significance here. Trout have 4 different pigments in their eyes, so their world is much richer in color than ours. It must be great to be a trout for a minute. Now, I'm sorry I can't help you imagine what it is to be a trout, but I can still show you some pretty pictures that will help you understand what a smaller color space would be like. Now, a 2-dimensional one or a 1-dimensional one. And this picture has no pale colors. It's saturated. And this picture is just built from different intensities of different shades of pink. So they're both in 2-dimensional color spaces. And this one is a 1-dimensional color space because all the shades of gray are just dimensional. Now, I can also prove to you a very exciting conclusion after we've made this discovery. And I'm going to show you how you can make any picture rather realistically using only 3 colors. And I've got Devon's phone and a microscope. This is a picture now. Wiring the microscope. Is that the picture?
Yeah.
Okay, so we got the picture of Spider-Man there. And if you zoom in, keep zooming in. Yeah. Picture is made of red, green, and blue lines, and they combine to give a Spider-Man. Now, you can understand how they combine looking at this diagram, and this is called the chromaticity diagram. It's a bit more complicated, but the colors in this diagram are of the same brightness. And it's constructed in such a way that between 2 points representing 2 colors, you get all of the different colors that can be made by adding the 2 together, like that. Now, it's supposed to show you all of the colors that you've ever seen, but that projector over there is using red, green, and blue light. So if you understand how the diagram is constructed, you'll see that all the different colors are actually inside that triangle. But still, we can imagine the rest, and we'll see what this odd diagram can teach us. Now, first of all, red, green, and blue are not physically primary, are they? We might have been led to believe that. They're just a wise choice given the shape of the diagram, which again is a human thing. I mean, if bees had projectors in 3-dimensional color space, they would probably use different pixels. Secondly, we can now answer our first question. The rainbow is special because it's on that edge, it's on that convex shape. That means that the colors of the rainbow cannot be made from any other different colors. On the other hand, pink is somewhere in the center. Now, also, colors of the rainbow and this strange line of purples enclose what we call real colors. the ones we can actually see. And there's no real light that will ever stimulate our eyes in a way that corresponds to a point outside of that diagram, which we call an imaginary color. There is a way to cheat, and after the show I can teach you how to see an imaginary color. But there's a way to end here. There's something to end on, and that's that. However many pixels you use, you can see there that you can never put a real rainbow on the screen. So enjoy your real natural rainbows.
Our next talk is our final talk, and there's a good reason it's put at the end. It's due to our shocking disregard for health and safety. If this had gone wrong, it would literally have had to have been the end of the talk. But unfortunately, we had visitors and we had to change it slightly. But we didn't want to change the running order, so I'd like to welcome Kyle to go talk about pendulums. So, a round of applause, please.
Pendulum. Riveting, I know. Okay, everyone's seen a pendulum before and they know what they do, they know what they're for. You see them in clocks, they used to keep time. But actually the physics of just a simple pendulum has some pretty far-reaching consequences. One of the interesting things about a pendulum is that the period, the time it takes to swing from one side to the other and back again, doesn't depend on the mass on the end of the pendulum. So, if I took this pool ball and swapped it out for a bowling ball, which I'm not allowed to do because of health and safety, then you'd actually see the period is just exactly the same. So the reason this is, we can figure out by just thinking about why the pendulum is moving in the first place. So it's moving due to gravity. I displace the pendulum to one side, when I let it go, the force of gravity pulls it down to the middle and keeps it swinging. So gravity is the only thing that's giving this any push. I know that because the only energy I give it is the potential energy when I displace it to one side. It doesn't get energy from anywhere else, and I know that because when I let it go, it doesn't swing any higher. And I can prove that while risking my teeth. That would have been way more impressive with a bowling ball. But we can think about why this pendulum is swinging like this. So it's swinging due to gravity. And you know that things that are more massive are heavier, they're harder to lift. So gravity's pulling on them more. So it seems reasonable to reason that something with a heavier mass on the end should swing faster because gravity's pulling on it more. But we've neglected something, and that thing is inertia. So inertia is a measure of how hard it is to change something's direction when it's moving, or to slow it down, or to get it started once it's already stopped. And bigger things have more inertia. It's harder to stop a truck than it is to stop a ping pong ball. And while the pendulum is swinging, on its upswing, it has inertia. And gravity has to overcome that inertia in order to slow it down and make it go in the other direction. So it seems reasonable to reason that something with more mass has more inertia, and so it swings slower. It's taking gravity a longer time to change the direction. So saying the pull of gravity is giving it a faster period, or a faster oscillation, and inertia is giving it slower. What actually happens is these two effects cancel each other out. And this is a reflection of what's called the equivalence principle. And this says that there are two ways of determining mass. You can determine it by seeing how much gravitational force there is, or you can determine it by seeing how much inertia there is. And as far as we know, these two things are exactly the same. There's no reason why they should be, they just are. And they've been measured to be the same to 1 part in 10 to the 13, which is about the same as weighing an elephant and then putting a grain of sand on its back and weighing it again. I mean, the difference is insignificant. Einstein, thinking about this, came up with his general relativity, because he said that the two masses are exactly the same. And that means that you can't tell the difference between being in a gravitational field or being in an accelerating frame. And if you sit and you think hard about this, and you're as intelligent as Einstein is, then eventually you come up with some theory of curved space-time, which is general relativity. So from a simple pendulum, you get to general relativity. Well, we can do something actually that's more fun now. So the mass doesn't affect the period of the pendulum. So the only thing that does is its length. So what I've got here is a demonstration called the pendulum wave. And you'll see that all the pendulums have different lengths. Now, it's designed so that the one at the front in a minute will complete 30 oscillations, the one behind that 31, 32, and so on and so on. And what will happen is as they all start together, eventually some will get in front, some will get behind, and you'll see this interesting waving effect. So it looks like they're all kind of going into a bit of a mess now, but actually the relationship is still quite strong. And because some of the pendulums complete an odd number of oscillations in a minute and some complete an even, you'll see at one point the reds will be going in one direction and the yellows will be going in the other. And again we get back into this mess, and eventually they will come back and be swinging together again. Now this isn't just an interesting thing to look at. You can actually use it as an analogy to some quantum states and how they evolve in time. So there you go. From a simple pendulum, you come from general relativity to quantum physics.
Well, that's the end of the evening, so hopefully you've enjoyed yourselves. The last thing I'd like to do is welcome everyone back on stage if possible, just to thank you yourselves, because I'm sure we've enjoyed putting the show together. Hopefully you've enjoyed it yourselves. Hopefully it'll come through all this fancy game. So hopefully I'd like to welcome all back on stage again.